6.5, dividing radical expressions. So what we never want to see is a radical in the denominator. So whether it's this lesson or the next one, we may end up needing to, I think they call it rationalizing the denominator. But we should never see radicals in the denominator. If you do that, I actually don't completely know why math nerds don't like that, but if you do, if you ever show a square root in a fraction in the denominator, it would be like showing a math nerd a decimal in a fraction, which, if you really want to make them mad, that's one way to do it. So dividing radicals, which we've seen, and in the past we saw this with square roots, but if you have a nth root of a fraction, you can split that fraction up into its own numerator and denominator with those roots. And also, if you have the nth root, again, notice that the index has to match for the numerator and denominator on these. If they do match, you can make that its own individual fraction with that index. We may go both ways on this one, right? Like this one goes this way, and then you can also go the other way too. There's uses for both, and if you see that maybe like these numbers can be simplified, it may be useful to simplify them. It may be. I notice again that 125 and 5, I can simplify those two. In fact, that it's going to help me to get rid of that 5 right there. So now I'm just going to write it as the square root. I can write that bigger. The square root of 125x over 5, right? And again, I'm doing this because the roots, they're the same index, they're square roots, and I notice that 125 and 5 can simplify. So let's take that 125 and the 5, and let's simplify them. I'm still operating inside that square root. Okay, so all of this is staying in the square root, but 125 divided by 5 is just 25. Okay, now we still have the x, and that's the square root of that stuff. Now, do you see any other values that can be simplified, just like we saw last time? Yeah, hopefully you see we can now break this up into the square root of 25 times the square root of x. And the reason why we want that is because the square root of 25 is 5, and then the square root of x is just still the square root of x. So that would be considered fully simplified. This one, of course, it works really pretty, it works clean, because we're just starting out. It'll get there, we'll get there. Okay, now on that last problem, we were looking at numbers, right? Like you'd look at 216, can you divide that by anything? Well, there's no other numbers in the denominator, but I do see some x's, and that's good. That's good too, because if I see those, then I can simplify them, right? So I got my square root still, but now it's a full square root of 216 x to the power of 11 over x to the power of 6. Now, I actually purposely put this x to the power of 6 beneath the x to the power of 11 because those are the values we're going to work with. Okay, now let's go ahead and separate these two, though. So you got square root of 216 times the square root of x to the power of 11 over x to the power of 6. Now, it doesn't matter which one you start with. I like to start with the numbers. And why am I doing 216 right here? Because I think it can be simplified. Can it be? I don't know. I don't know for sure. Here's what I know, though, is looks like I can divide it by 3, which would be 72 right there, which is not a perfect square.
6 and 36.
So, yeah, 6 and 36, right? Now, could I divide anything between that? So is it divisible? 4 doesn't really help us because 36 is a bigger one. But it would be divisible by 4. Let's see what that is. That'd be 4 and, yeah, thank you, 54. But again, 4 is a perfect square, but it's not bigger than 36. We want the biggest one. 5, it's not divisible by 5, so that doesn't work. So 6 and 36 looks like that's the best one that we have. And so 216, again, we're going to look at it as the square root of 36 times the square root of 6. And the square root of 36 is 6. So now I have 6 times the square root of 6. Now, differentiate these two 6's, right? Like the green 6 came from the square root of 36, and the square root of this purple 6 is still in the square root. All right, so that's the numbers part. And by the way, if you just typed in the square root of 216 in your calculator, it would have given you 6 times the square root of 6, which is legit. It's a legitimate way to do this problem. But now we got to deal with those x's, right? So that's division of the base x's. So I am going to take the x base, we're going to take the 11 and then subtract the 6. And it does have to be in this order. It's always numerator exponent minus the denominator exponent. So that would give me then the square root of x to the power of 11 minus 6 is 5. Okay, so I'm going to move this over here so we can do some work. So the square root of x to the power of 5, again, as an exponent, I would show this as x to the power of 5. But we would have to take that, and then that square root right there would take the 5 and divide it by 2. Now, if you do that, you'll get x to the power of, 2 with a remainder of 1. Right? So that then tells you got x to the power of 2, and then that remainder of 1 is a square root of x. Just make that red. Okay, so we have everything simplified. Let's go ahead then and combine our stuff. So on the outside, I would have the 6, and I would have the x squared.
I have a question.
So yeah, that, so I'll finish this one here. Right, we still have got some square root stuff going on. We have the purple 6, and then we have that square root of x. Put that one orange just to kind of relate it. So that should be our simplified answer. But yeah, let's go back to that 5 divided by 2. So I showed it with straight division right there. I kind of wanted to show it with long division, just so we know that we're looking for a remainder here. But yeah, you could have shown it as 5 divided by 2 like this. Yeah, I don't know if that's a better 5, but it's a 5. Yeah, either of these ways to show this square root, either of these are good. Okay, why are these letters being used? I don't know, but the thing you need to notice on this is that the index is the same, right? So if you're multiplying values that have the same index, you can combine them into the same root with the same index. Now, if the bases are the same here, you can still, and this goes back to more exponent rules, but you can add those if you wanted to as well. You can do it this way. You can say, well, I'm going to take a to the power of j over m, and then this one would be a to the power of m. Oh, it's supposed to be an n. I apologize. Not n, not m, but n. It's supposed to be an n right there. See, and what happens here is that you can combine these bases by taking, because they have common denominators of n, and then just do j plus m. Now, whether you go this route, which then kind of leads back to this route, is okay. I think for the most part we kind of go this way, though. So we're looking to make these fractional exponents, and then we combine them if the denominators are the same. If not, we can force those denominators to match. So keep that in mind. This takes us back to some fraction stuff, which, by the way, the calculator will do. So at this point, if you saw you're just going to add the exponents, you can put it in the calculator. Even if the denominators don't match, it will give you the simplified fraction from that addition. Rationalizing denominators. So this goes back to, we don't want square roots or roots. We don't want any roots in denominators. So please do not put them there. But we can force them to go away on our own. So kind of like what we saw in that last one. But now it's not necessarily a principle of equality with these ones, but you just need to remember. So remember, let's go back to a common fraction like 1/2. So to rationalize denominators, what we're going to be doing is we're going to be multiplying something. And again, the process is essentially the same, but now the work, it's kind of different work, right? So if I wanted to scale this up, I could say, I just want 2 times 4 to get a denominator of 8, if I wanted a denominator of 8. But if you do it to the denominator, you need to remember to do it to the numerator. So notice it does not change the value of the fraction. It changed the way that it looked, but not the overall value. And that's the key part to scaling fractions like this. Now, with that, would that have mattered if I multiplied it by the square root of 4? It wouldn't. I mean, it changes the value. It's not now 4 over 8. You'd get something else, which we're going to get into. But to rationalize denominators, we're going to have to multiply these by square roots, both in numerators and denominators. That's what we're doing. yeah, we're kind of like trying to find common denominators. What else does it say? You have to determine what to multiply the denominator by to make the radical go away. So you are forcing this to happen. You are taking control of a fraction and not letting it destroy your life. So this requires multiplying numerators and denominators. That's what I'm showing right here is in this example, and then making the exponent of the radicand match or be multiple of the index. The reason why that will happen or why that's useful is because we're dividing the exponent by the index, and if I can make that a whole value, all the better. So rationalize the denominator, no problem. What I need here is not a square root, right? In the denominator specifically. I do not want a square root in the denominator. Now this 13 is kind of a weird number, right? Prime. I don't know if that makes it pretty, but what I would like to do is to get that denominator to not be a square root. So how are we going to make that not a square root? I'm going to take that square root of 13 and just multiply it by itself. Okay, because the square root of 13 times the square root of 13, I can make that the square root of 13 times 13, which is the square root of 13 squared, which is just 13. So that makes the denominator just a 13. But don't forget, if you do it to the the denominator, you got to do it to the numerator as well. And now in the numerator, I've got 52 times the square root of 13. So I'm going to show that here, 52 times the square root of 13. Now, if the 52 and 13 can be simplified, then I should. And as it turns out, 52 is a multiple of 13. 52 divided by 13 is 4. So that part right there gives me 4. And then I still have multiplied by the square root of 13. And that would be considered fully simplified right there. Now, sometimes students just stop right here. It's like, hey, look what I did. Because we're not really familiar with, dividing by 13. Put it in the calculator, 52 divided by 13. And it'll tell you it's 4. So make sure to do that. Now, that's one way to do this, okay? And that's showing some work, which we like or don't. But what you could have done is you could have used the calculator method on this one, I think. I'm going to try it. So 52, I'm using the Enter D button, square root of 13, enter. Boom, they gave me 4 times the square root of 13.
Even on the exam?
You got to show some work on an exam, though. For these, if you have a square root in the bottom, usually it just kind of matches here. I had the square root of 13. I would almost always expect the new denominator to just be whatever was inside that square root. Now, you could simplify those if you wanted to, but usually if we just make a match, then we can kind of factor out from the top by itself. Well, hopefully it will. So this one. We do have a number 1, and we got some index and exponent right there. But I can't really simplify from just the numbers, right? So what I would like out of this, because, and that's kind of a large index right there. It's really not a problem, you guys, because what I'm going to do is I'm going to show it as j to the power of 6 over 13 right there. What I would like this to be is j to the power of 1. So, you know what, I might have to do this 2 different ways, or show it 2 different ways, but it's the same thing going on. Now, if I were to make this j have a power of 1, which is what I'm going to do, what do I got to apply to my 6/13? Well, you'd have to add in 13ths 7/13. How did I know that? Because 6 plus 7 is 13. This would then give me j to the power of 6 plus 7 is 13 13ths. And 13 over 13 is 1. Okay, now that's applying that to the denominator. But if I do it to the denominator, I must also do it to the numerator. Doing that, though, would mean I'd have to take the 1 and multiply it by j to that new power, 7 over 13. Now, this is strictly using exponents right here. The other method is to use the actual roots, which I will show. So now I've got j to the power of 7/13 over j to the power of 1, which I will now show is just j. Boom. Now, that's good enough for me, but what they probably want here, since we started with a root, is an answer that also has a root. So I've got my j there. So this would be, it's going to be the 13th root of j. That's correct, j to the power of 7 from the numerator on the exponent right there. So I believe that's what they want. I believe they want this one. It's possible they want this one, but they did say to rationalize the denominator on this one. So that rationalizes it. I almost want to say that it would accept both. I just can't confirm that it would. But either one of those would work. Now, the other way, like I was saying, so let's go back to the original. So we had 1 over the 13th power of j to the power of 6. So what I did there, this part right here, you would need, so I'm going to show, again, probably more work than you'd want to show, but if I multiply this by the 13th root of j to the power of 7, see, now I can I'm still working in the denominator, by the way. It's just if I do it to the denominator, I got to do it to the numerator as well, right? So that'd be 1 times the 13th power of j to the power of 7 as well, which we see in this numerator, right? So how does this stuff become just an individual j? Well, in the bottom there, now that I have matching indexes, what I can do is just make it one individual index of 13th root of what would be j to the power of 6 times j to the power of 7. And there we can see then that we can add those exponents together. So it ends up being the 13th root rather, of j to the power of 6 plus 7 is 13, right? Because we're adding those exponents. So 13th root of 13 exponent gives us just that regular j to the power of 1. So that's where that j came from. Or this one, whichever one you're looking at. I could show more work here, not that I think you want me to. But, right, so that would have equaled, you still would have had the 13th root of j to the power of 7. And then finally over here, still with that numerator, the 13th root of j to the power of 7. But this part right here, 13th root of j to the power of 13 just ends up being j. And again, you see this format at least is still written like this one. Same thing, I suppose it actually is the same work, just shown with roots instead of exponents. It's up to you. So rationalizing the denominator, this one's a full root, and you know, if you're like, you know what, I really would like to separate these, and feel free to do it. Now you can do that and then work from there if you want to. I wouldn't, and here's why. It's because you got some y's and b's right here that should undo each other or become phantom ones with each other, or in other words, you can apply the exponent rules on these. So that's what I'm going to do. So I'm going to go down this way. And I will work from within. Now the 2/7, I don't see that can be simplified, so I'm not going to worry about that. We will later. We will worry about it later, but not right now. Okay, so again, just focus on one part at a time. So I'm going to focus on my y's. Okay, now that would be a y. This is division, so I know I'm subtracting the exponents. That's going to be 9 minus 4, which will end up being y to the power of 5. Okay, so that's my y's. That'll be in the square root, which I'll show here in a second. And then I've got a base b with the power of, and they're dividing the bases, so we're going to subtract the exponents, 2 minus 7, which would be b to the power of negative 5. Now this negative 5 here tells us that it just goes in the denominator. So right now I have the square root of 2/7 y to the power of 5, b to the power of negative 5. But I'm going to rewrite that as still a square root, but as a fraction. I got the 2/7. But in the numerator would have y to the power of 5. In the denominator, since it's b to the power of negative 5, I can just put that in the denominator. Now I got a positive exponent right there, which is good. Now, at this point, I would separate them, the numerator and denominator.
What was the b to the power of negative?
I made this a positive 5 exponent. Some students could work with that negative exponent, negative 5 exponent. But I prefer to see it like this because I can see right here that I can actually pull some b's out of that denominator, right? So at this point, of course, there's still lots of different directions you can go from here. But I'm going to separate these, okay? So I got my numerator, which is 2 times y to the power of 5. And this is all over the square root of 7 times b to the power of 5. Now you can rationalize the denominator one value at a time, meaning if you want to rationalize the 7 first, feel free to do that. When you do so, you should end up with, in the denominator, just a regular 7, not square root of 7. So how do you take a square root of 7 and make it a regular 7? You'd multiply it by the square root of 7. See, because this is the square root of 7 times 7, that's the square root of 49, which is this 7 right here. But if you do it to the denominator, you must also do it to the numerator. So I'd have to take the square root of 7 times 2, which would be the square root of 14. Gonna move that over a little bit. So there's a little bit extra space. Okay, so that's nice, but what about the b, right? Because we don't want that b to the power of 5. Well, this is really the square root of b to the power of 5, which is also b to the power of 5 divided by 2. And that then would be b to the power of 2 with a remainder of 1. So that would be, in other words, b squared times the square root of b. I did skip some steps between this one and this. Okay, so from there, I don't need to get rid of the b squared, right? That's rationalized. It's the square root of b that I've got to get rid of, essentially. And so at this point, I would have to multiply that by the square root of b. But if I do it to the denominator, I must also do it to the numerator as well. Okay, so that's the square root of b times the square root of b, which is the square root of b squared, which is just another b. So let's see if I can gather my work together here, make it look a little bit more pretty, a little bit. And by the way, I still have that square root of y to the power of 5 in the numerator.
Are you taking out the b? Wait, why are you taking out the b?
And that's shown in this work right here, the square root of b squared, which is just b. So what do I got now? So from here, in the denominator, I've got 7, and I'm going to show more work here, but I've got the b squared and the b, so that's 2 b's. I got a b squared and a b in the denominator there, so I'm going to combine that into a b to the power of 3. So I still got my 7, but that'd be b to the power of 2 plus 1, which is going to be b to the power of 3. Now that did rationalize the denominator, but what do we got in the numerator? We still got to worry about that stuff, right? So let's work in just the numerator. So I'm going to have my square root, and I've got my 14, and I've got my b, right? Let's look at this square root of y to the power of 5. And again, we should always be looking to simplify if we can, but this would be the same. What the heck, I'll use purple. So that'd be y to the power of 5 divided by 2, which is the same as y to the power of 2 with a remainder of 1, right? 5 divided by 2 gives you 2 remainder 1. So that would be the same as, I have enough space? Yep. That'd be the same as y to the power of 2 with the square root of y. Okay, so from here, then, I've got my y to the power of 2 in my numerator, but I still have a square root of y which needs to go in the numerator. So let's write that out here where it's been simplified. 14. Yeah, so it's pretty ugly, by the way. Some students would say, wasn't this prettier than this one? Perhaps. But that's not what they want. They want this rationalized in the denominator. So we got y squared, square root of 14, by, all over, 7b to the power of 3. And as much fun as that was, because you enjoyed it so much, that's as far as we need to go. These types of problems, it's all about what are we trying to get out of this? And it's like the answer to me, it's pretty ugly. It's a pretty ugly answer. But it's about getting that square root out of the denominator. So yeah, even at this point, multiplying by square root of y, you'd have to multiply in the denominator, which places that square root of y back into the denominator, which we don't want. And so again, our goal was just to make that denominator not have square roots. And again, you're now equipped. You can see, you can work with the numbers, you can work with the letters. If we had kept the y's here in the denominator, by the way, you could work with that as well, right? You could say, well, this is y to the power of 4, which would have been y squared. And then y to the power of 9 would have been a y to the power of 4 here. And then 4 minus 2 would have given you that y squared in the end anyways. But then you would have had the square root of y in the top. Is that a better method? I don't know. Again, it's just a different path to take to get to the final answer. But all of those work within the rules that we have, right? And that's the main thing is the math. It is what we want it to be if you'll take control of it using the tools that you have been equipped with now.